that episode, you saw some mathematicians who were trying to solve the Riemann hypothesis, or really prove the Riemann hypothesis. So here I've written out what the Riemann hypothesis is. It's that this function called zeta is 0 only at the negative even integers and complex numbers whose real part is 1/2. So I'm going to unpack this kind of confusing notation that you probably haven't seen before. But the major point here is that this was proposed by Riemann in the 1850s, and it's still unsolved. So that's why it shows up in a lot of TV shows and movies that are looking for a really hard math problem. If they really want something that has not been done before, they like to use this problem because it has no solution yet. No one has been able to prove this. So what does all this notation mean? First, let's talk about the different kinds of numbers that show up. So these, you may not have seen this notation before, but you've probably learned about all these objects. This fancy n, or blackboard n, stands for the set of natural numbers, or some people might call them the counting numbers. So starting at 1, 2, 3, 4, 5, and so on. So up here we're saying that if you take a counting number, multiply it by -2, you're going to get 0. Which we know that part is true. It's the other direction that's hard to prove. All right, the next set of numbers that we could talk about is the fancy z, or blackboard z, and these are the integers. And these are just all of the whole numbers, so not just the positive ones anymore, but it includes 1, 2, 3, 4, 5, and so on. But it also includes 0, -1, -2, -3, and so on backwards. All of your whole numbers, positive, negative, and 0. From there, we could build to the rational numbers, which are fractions of integers. So this is anything that can be written as p divided by q, where p and q are integers, but also you can't divide by 0, so the one on the bottom can't be 0. Those are our rational numbers. The next major category is R, which is the real numbers. And there's lots of complicated ways to define this, but really for our purposes, this is going to be anything that doesn't have the square root of -1 in it. You can think of it as all decimal numbers. So whether they repeat or terminate, or they never repeat and never terminate, these are all going to be real numbers. And then finally, we have C for the complex numbers. And this can involve the square root of -1. So this is anything real or imaginary. So A and B can be real numbers, and I is the square root of -1. If you can write it like this, it's a complex number. That's what we saw up here. We saw a complex number where the first part was a half, and then the second part was anything with a square root of -1 in it. So the Riemann hypothesis is that these are the only ways to get 0 out of the Riemann function, Riemann zeta function, which we haven't talked about what that is yet. We know that it's 0 for these numbers, but the hard part is showing that that's the only place it's 0. So let's talk about what the Riemann zeta function is. In order to do that, I'm actually going to talk about another function first. So there are two functions here. There's the gamma function, which can be used to build the zeta function. And this is a Greek capital gamma. And if you have a natural number, it's actually a familiar function. So if n is a natural number, this is just factorial. But factorial only makes sense for whole numbers bigger than 1. And so we have to expand that definition when we're talking about other types of numbers. So if we're talking about just a general real number, any decimal or fraction, then we give it this really funky calculus definition that you don't have to know, but I'm going to write it down for you. So it's the integral from 0 to infinity of t to the x minus 1 e to the minus t dt. So if you've taken calculus before, especially calculus 2, you would have seen integrals like this. If you haven't, don't worry about it. The gamma function will come up in our definition of the Riemann zeta function. The Riemann zeta function is always denoted by the Greek letter zeta, which I'm terrible at drawing, but pretend that looks like a zeta. And if you don't know what zeta looks like, then you'll be surprised when you go look it up. It doesn't look much like that. But anyway, the Riemann zeta function, we can build it up to the complex numbers. There are some easy ways to think about it if you have easier numbers. So if you are plugging in a natural number, it's actually an infinite sum. The sum from 1 to infinity of 1 over k to the n. So this can be our definition if all we want to do is plug in a positive whole number. If I want to plug in a positive real number, then I can define it as 1 over gamma of x times another integral. So this is our definition if we have a real number that's greater than 1. Then we can define zeta of x as 1 over gamma of x times the integral from 0 to infinity of u to the x minus 1 divided by e to the u minus 1 du. Again, you don't have to know how to compute any of these things. They're very complicated functions. Just showing you what kind of math is involved. We're going to do 2 more generalizations before we get to the most general look at the Riemann zeta function. So the next one is if we take a complex number, s, then it's going to be 1 over 1 minus 2 to the 1 minus s times the sum from 1 to infinity of negative 1 to the n minus 1 over n to the s. So this is for complex numbers with real part positive. So that would mean, say, s is a plus bi and a is positive. And this looks very similar to what it works, or how it works for natural numbers. You're getting this infinite sum of powers of the number, but there's this extra factor at the beginning, and it's actually an alternating sum. The most general form is obviously going to be the most complicated. So this will work for any complex number. Zeta of s is the same factor, 1 over 1 minus 2 to the 1 minus s. Then there's going to be 2 sums, so stick with me. There's the sum, where n goes from 0 to infinity, of 1 over 2 to the n plus 1 times the sum, as k goes from 0 to n, minus 1 to the k, n choose k, k plus 1 to the negative s power. So this definition works for any complex number s. So what is the Riemann hypothesis saying? This is the definition of zeta of s. The Riemann hypothesis is asking you to solve zeta of s equals 0. So it's saying set this weird formula equal to 0. So it's saying solve for s. That's what the Riemann hypothesis is asking you to do. And it's a hypothesis because Riemann had a guess. Riemann thinks that either s is a negative even integer, or s is a half plus some imaginary term. This is what Riemann's guess is, because he knows that those work, but he doesn't know that there aren't any other solutions. You have to find all solutions for s. Here are some of them. Are there others? That's the question. And this is a really, really hard equation to solve. Mathematicians have been working on it for almost 200 years, and we still don't know if there are any other solutions. We can't prove that there aren't any others. And that's what the whole problem is about. This isn't the only television show that uses the Riemann hypothesis. I think that it came up in Glee, and it has come up in other movies. It gets a mention anytime someone needs a real math problem that hasn't been solved. So if you can solve this equation, you're going to be rich and famous forever. But no one has done it yet.